everyone, in this video we are talking about the assumption we impose on our linear regression model. As I mentioned when you're reading the textbook, we have a total of 6 assumptions. In my lecture, I want to emphasize 5, and I will explain why one of the assumptions is not something I really want to emphasize here, but it actually is very important in terms of interpreting your model result. Okay, so the first assumption, since the model we learned is called a linear regression model, that means we are assuming every x variable has a linear relationship with my y variable. Okay, so that's what we assume. Is that true? Right? So how about it is not true, right? So therefore here, the assumption one we try to understand is try to see if our model has a linear relationship. And also try to understand, does that making economic intuition sense? X should relate to Y, and do we including all the relevant predictor variable? And then also, if it is not linear, are we incorporating the non-linearity in my model? So the way we're detecting if this assumption is validated or not is just using a scatter plot using the vertical axis as my Y and the x-axis as my x variable, and we're going to creating multiple scatter plots. So basically, if your regression model have 5 axes, you will creating 5 scatter plot to see if x and y actually will show you that linear trend, or you actually see a curvature, right? So linearity is justified if the residual are randomly dispersed as well. So you also can use a residual plot to detect it without using the scatter plot x versus y. Okay, so if you do see a curvature in your trend instead of a straight line in your scatter plot, what you're gonna do? That is something we're gonna look at later in this module. Is we can introducing the higher order to my model so that I can capture that the nonlinearity. So this assumption is straightforward. As I said, it's a linear regression model, so the linear relationship has to be satisfied. And in order to correct in the nonlinearity, it's pretty straightforward. It's something we're going to learn after this lecture. It's related to the adding the high order to my models. Okay, this is the first assumption. Now I will show you the example. Okay, look at this data. I am showing you a simple linear regression. So sociology wished to study the relationship between age and happiness. So he interviewed 24 individuals and collect data on each person's age and happiness, where happiness is measured on a scale from 0 to 100. So of course, the age and happiness both are quantitative data or numeric data. So now we're gonna do a scatter plot using age versus happiness to see, we see the linear trend or non-linear trend. Okay. On the left-hand side, what I'm showing you is our scatter plot, x versus y. As you notice that instead of a straight line, which is supposed to be the trend line here, we actually see a curve. So in this situation, we understand our assumption 1 is violated. X and y are not linearly associated. And then we also can creating a scatter plot here as well for the residual plot. And we also notice that it's not evenly distributed around this 0 line, but I see a curvature. So in both situations, it's indicating my data, my model, when I use a pure simple linear regression model, it is actually violating my assumption 1. So the way we are correcting the mistake here, we will show later, is introducing the higher order to my model. Okay, assumption number 2. There is no exact linear relationship among the predictor variable, or in another term, is there is no multicollinearity. So basically, as you are using multiple x variable in your regression model, if your goal is try to understand how x impacting y, we do not want to have multicollinearity problem. That means if your x variables are highly correlated to each other, so that is when we don't want to have it. If your goal is try to understanding the relationship between x and y. However, if your goal is trying to predicting the y value, you don't care about how x impacting y, you just want to make sure if you can build in the model that if you know x, you can very well predict y. If that's the goal, then multicollinearity is not a problem. So that's why nowadays in the data science world, most of the data science project, the goal actually is just trying to understand if I'm able to predicting y. So if that's a goal, don't worry about the multicollinearity. You don't need to take any action to correcting the multicollinearity. However, if you work on some project, try to understand if x actually impacting y, or X and Y have some correlation. So if that's your goal, you have to handle the multicollinearity problems. Okay, now the question is, how can we detect the multicollinearity? Okay, so after you estimate your regression model using the normal way, check on your R square, check on your significance F. So the high R square, high significance of the F test with the individual insignificant predictor. So basically, your R square is very high, larger than 50%, and also your F test showing very significant. But as you look at individual variable, X variable significant, you will notice certain X variable are not significant, but you think, wait, I think intuitively that one's supposed to impact in my Y, but somehow it doesn't. So in that situation, you need to check that means your model had potentially had the multicollinearity problem. Okay, so or sometimes you look at the sign of your X variables is incorrect. So for instance, if you look at what affecting the weight loss, and you notice there is a variable is how many hours of exercise you did that day, but the more exercise you do, and then the lower weight you will gain, you will have, right? So there is a negative relationship. So the sign should be negative, but somehow you check your model, it's positive. So but your R square is very high, your F test is significant, but somehow that variable sign is incorrect. So in that situation, also indicating you might have multicollinearity problems. So how can we do it? So the way we will do it is we're going to drop the one collinearity with the other variable that is not important for your model, right? Or you can add in more observation to your data. That's another way to solving the multicollinearity problems. And I also list the do nothing here. Again, do nothing. We will do nothing if your goal is just try to predict the Y instead of trying to understand the relationship between X and Y. Okay. Now let's look at example together for the assumption 2. Okay, a linear regression model that uses median home value as a response variable and the median household income, per capita income, and percent of owner occupied home as a predictor variables. So as you notice that basically we try to understand what will impact median home values. So before we look at the result, and you will know that the median home value should positively relate to median household income, should positively relate to per capita income, should positively relate to the percent of the owner occupied home, right? So if you think about those, so they all should be positive sign. As we move on here to look at the model result, first of all, we notice that my R square, in my first model, I'm including all the X variable, right? So the household income, the per capita income, and the percent of the owner occupied. When I'm including all of them, I have very large adjusted R square, 80% of variation that can be explained by my model, right? However, if you look at the model, so the per capita income, this is supposed to be significant, right? But actually it's not. In the second, if you look at the sign, except the household income is positive, the other ones are negative, impacting on the median home value, which does not make sense. So this is the moment you said, you know what, I might have multicollinearity problem. So therefore, we are trying more models by eliminating certain variable from my model, right? So I first eliminated per capita income, and then my household income still positive, significant, and then my percent owner occupied become negative. And so if I eliminating the household income and per capita income becomes significant and positive, so this makes sense, right? So the problem here is the household income and the per capita income might highly correlated. So the best model would be just including one of them that will be able to solve the problem. Okay, so this is the second assumption. And the third assumption is called a conditional on the value of the predictor. The variance of the error term is the same for observations. So basically what they say, the model we are having should have no heterostochasticity problem, has to have a constant variability. And then when this assumption is violated, what happened is we can no longer trust the T and F test because our standard error was not properly estimated. So the question is, how can we detect it? So we can detect this assumption whether they are violated based on our residual plot. So if we know this assumption is not violated, we're supposed to see a horizontal band. Okay, horizontal band. And then if it's violated, you will be able to see that the residual either the span, the disperse will increasing or decreasing. So that is when we know our assumption is violated. So the question is, how can we correct it? So we can correct in the standard error or by using white robust standard error. So we don't learn how to do getting the robust standard error here, but if you're taking my applied econometrics, we're actually going to learn how we can get that standard error. And then so one thing emphasized for this assumption is to make sure you know based on the residual plot, you know how to detect the assumption is violated. Okay, so look at this example. So we look at the simple regression that relate the store's monthly sale to its square footage. And after we run the regression, we are able to obtain the residual plot. The vertical axis is the residual, horizontal axis is the predicted sale. And then as you notice that instead of a horizontal band, okay, if I draw it, instead of horizontal band, we see this kind of comb shaped, right? Or wedge shaped. So in this case, it means the dispersion of my residual is increasing, okay? We also can see the opposite situation, starting with very wide and then start to getting very narrow. So both scenarios consider this assumption is violated because we don't see that horizontal band, okay? Next, assumption number 4. So we assume conditional on the predicate variable, the error term is uncorrelated across observations. Basically, there is no serial correlation. So actually, after we learning regression model, we're going to move on to the time series analysis. In that model, many of the model we learn in that module is going to be suitable for the data that actually has serial correlation. Okay, but make sure you know when you run the linear multiple regression model, we don't want to have the series correlation. Okay, when we have the series correlation, our standard error are inappropriate. So that means our F and the T test that are testing the significance are no longer reliable. Okay, so how can we test out if we have this kind of problem? So our main goal is try to creating this called residual versus order observation plot, trying to see if we are able to see some kind of big U shape. Okay, if we don't see the big U shape, either upward or downward big U shape, that means this assumption is not violated. Okay, the remedy will be using the new West robust standard error. It's in R in Python. Again, in this class, we're not focusing on this. So if you take applied econometrics, we can dive in further in terms of how to correcting these mistakes, this violation. Okay, so here I'm showing you the example. So it's a considered model that use advertising and the unemployment rate to predict the sale of the sushi restaurant over time. Okay, so in this residual plot, it's not traditional residual plot. We call it residual versus the order of the observation. So basically, the horizontal axis is time, t. And as you notice that we do see the big U shape. See, this is the one big U shape, and this is the second big U shape. So when we are seeing the big U shape, that means this assumption 4 is violated. Okay, so as you see here, we see big U shape, therefore the assumption is violated. Okay, the assumption 6, again, we skip assumption 5. I will talk about it after I finish assumption 6. So assumption 6 is the error term is normally distributed. And so when we are building the regression model, we assume our error term is normally distributed. And so that we can use our interval estimate to do hypothesis testing, etc. So this is an important assumption. So how can we test it? We basically use the normal probability plot coming out of our Excel output. So if the assumption is not violated, and we will be able to see this kind of straight line. Okay, a straight line. So all the points should fall approximately along a straight line. So if it's not for approximately straight line, that means we might have outlier in my data. So how can you solve it? So one of the simple way to do it, just increasing your sample size. Okay, increasing your sample size. Okay, so these are the 5 assumptions we want to emphasize in our class. Like I said, we skip one from your textbook. So when you're reading the textbook, we have assumption 5, so which is talking about your X variable are not correlated with your residuals. So so if your x variable is correlated with your residual, what's going to happen? So one of the many important tasks in the business world is try to understand whether changing x will cause changing y. Okay. So when we run the regression model, we only can prove x are correlated with y. We cannot prove x cause y. So in order to show x actually cause y, you need to eliminate one possibility, that is your x variable are correlated with your residual. So if your x variable is correlated with your residual, you cannot say x cause y. Okay, give you an example. So let's say we try to understand what are helping people earn more salaries. So you including all the variable you think you needed, you can collect it, especially you including one is going to Ivy League, right? Going to Ivy League. And then you will find there is a positive correlation between going Ivy League and making high salary. But at this point, but you cannot conclude that going to Ivy League causing you earning more salaries. Why is that? Because there is a very important variable is hidden. We did not include it, which we also cannot measure it at this point. So that is your ability, your capability to work, right? So going to Ivy League is highly correlated with your ability to work a great work, right? Since you grew up, you're working towards in the Ivy League, you're gonna do so many things, so you might have a better capability to do the work, and then also have a better capability to do the work also is correlated with our y variable, which is a higher salary, right? So having a higher capability causing you having a high salary, so that will be a causal relationship. However, when we build in the model, since we are not able to measure the capability, we only able to measure whether you're going to Ivy League or not. But going to Ivy League also correlated with your capability to work. So therefore, make you thinking. We will found going to Ivy League is highly correlated with you making a high salary. But you cannot say they have a causal relationship because we cannot we will found our assumption 5, which is your y variable is not, your x variable is independently from your residual. That assumption in this scenario is violated, so that you cannot prove causal relationship, right? So why I don't want to include this as a part of my assumption, because in the business world, not all the time we try to prove causal relationship. Most of the time we try to understand whether they are correlated, and most of the time we try to understand, are we able to predicting why. If we violating assumption 5 that's listing on your textbook, it still serve the business purpose. You just need to make sure you understand you cannot prove causal relationship, right? So therefore, I think that assumption is important, but if you violating that assumption, it's not detrimental for your model. It's just impacting on your interpretation of the result, right? So therefore, I put that assumption on the side because I don't think that's assumption we should put on all our linear regression model. It's when you are thinking using a linear regression model to prove the causal relationship, that's when you need to be careful on that assumption. Okay, so in our next video, we're going to look at the model building, the quadratic form, the Cobb-Douglas function, etc. So hopefully you are enjoying the last part of the regression analysis, and after that, we're going to move on to the other analysis. Bye.